Hello everyone, today let's take a look at QP111 where we're basically just going to derive the whole exponential distribution. And it actually shouldn't be too hard once we know the Poisson distribution from quantipose number 1, right? Basically in this question we have small asteroids that strike Earth randomly over time, and evidence suggests that impacts occur independently and at a constant average rate of 12 impacts per hour. So we have a Poisson process here because we have independent events at a constant average rate. So we derive the Poisson distribution in quantipose number 1, and now we are letting t be the waiting time in hours from t equals 0 until the first impact that we observe. So part A, what is the probability that the first impact occurs within the first 10 minutes of observation? So t is the waiting time until the first impact that we observe. We're trying to find the probability that the first impact occurs within the first 10 minutes. So we're just trying to find the probability that t is less than or equal to basically 10 minutes. Now we're basically following a Poisson process with a constant average rate of 12 per hour. So I'm just going to call lambda and I'm going to set that equal to 12 impacts per hour. Now we want the probability that the first asteroid strike occurs within the first 10 minutes right here. Now you can see that we're modeling a continuous function, right? Because we're dealing with time now. So because it's continuous, my first event could happen right here, or it could happen right here, or it could happen right here, or it could happen right here. It could happen anywhere on this interval, obviously. I could also have 0 events occur within this interval, or I could have multiple events occur within this interval. So maybe my first impact is right here, and then I could also get a second impact right here, or I could get a third, or I could get a fourth, or I could get a million impacts, right? Basically, the thing to realize here is that asking the probability of the first event occurring within the first 10 minutes is just basically like asking what is the probability that at least one event occurs within the first 10 minutes. That's how we can relate this to the Poisson. If I have exactly one impact occurring within the first 10 minutes, then yes, the first impact did come within the first 10 minutes. If I have exactly 2 impacts occurring within the first 10 minutes, then yes, the first impact still came within the first 10 minutes, right? This is just obviously because if we have multiple events occurring within a window, well then obviously there's going to be a first one. Okay, now just to write it out, because this is really the key fact, but the probability that t is less than or equal to 10 minutes is just the probability that the first asteroid impact occurs within the first 10 minutes, and that we can model as the probability that at least one impact happens within the first 10 minutes, which is Poisson. And again, we know that this follows a Poisson distribution from QP1 because we're modeling the number of events basically within a time interval when these events occur independently and at a constant average rate. So if we let x be the number of impacts within the first 10 minutes and our rate parameter here is 12 impacts per hour, again, just like we did in QP118, if we know that events are occurring at a rate of 12 per hour, well then we know that they're going to be occurring in a time window of 10 minutes at a rate of 2 per every 10 minutes. We know that obviously because we have 6 different 10-minute subintervals within an hour, and events are occurring at a constant average rate of 12 per hour, so that just basically means that they're occurring at a rate of 2 per 10 minutes. So events occur at the rate of 2 every 10 minutes. So what is the probability now that x is basically greater than or equal to 1? Where x is the number of impacts within the first 10 minutes. Again, we know that the probability that the number of impacts within the first 10 minutes is greater than or equal to 1 is the same as the probability that the first impact comes within the first 10 minutes. This right here is just going to be easier to calculate if we understand that it's equal to 1 minus the probability that 0 events occur within the first 10 minutes. Since x follows the Poisson distribution with parameter lambda equal to 2, well, we derive this in QP number 1, the density, or sorry, the mass function of that is basically going to be e to the power of negative lambda, in this case it's 2, times lambda to the power of x, in this case lambda is 2, so 2 to the power of x over x factorial, right? So now the probability that x is equal to 0, we can just plug in 0 into this equation right here. This term will be 1 and so will this one, and we'll just be left with e to the power of negative 2. So the probability that x is equal to 0, well, this whole equation right here will be 1 minus the probability that x is equal to 0, which is e to the power of negative 2. So that's the answer to part A, the probability that the first event occurs within the first 10 minutes, which we just know is going to be equal to the probability of at least one impact in the first 10 minutes, which is Poisson distributed, just like we did in QP118, and then we can just find this based on that Poisson, right? When you actually work this out, you get something along the lines of 0.864%, so 86.4%. That is the probability that at least one event occurs within this subinterval, which is what we would expect. We would expect it to be higher because we are expecting 2 events to occur within that subinterval, right? And now part B should be pretty simple. Once we have done that already, we're just generalizing to find the probability that t is less than or equal to any value of t, right? Again, this is just the probability that the very first event occurs within the first t amount of time, where t is like a subinterval. If I call y the number of impacts in the time interval of length t, then we know that this is going to be Poisson distributed, and we can relate it to this. This is just going to be the probability that y is greater than or equal to 1, right? So the probability that at least one event occurs within the time interval of length t. And again, this is Poisson. We know that this is just going to be equal to 1 minus the probability that y equals 0. Now it's Poisson, but what is our rate parameter lambda? Well, in this case, we have a time interval of length t, right? If we have lambda equal to 12 per hour, well then if we have a time interval of length t, I'll call it in terms of like fractions of hours, right? So like for instance, in this case, we had basically 1/6 of an hour, t equal to 1/6. So what did we do? Well, we multiplied lambda by t. So if we're looking at a time interval of length 2 hours, well, then we would expect lambda is 12 times 2, 24 different events that happen within 2 hours. If the interval was length 30 minutes, well, that's just 1/2 of an hour. So we multiply lambda 12 by 1/2 and we get 6 events per hour. So this is exactly what we want. So this right here is the rate parameter that we can use in our Poisson PMF. So we know that the probability that y is equal to 0 is just going to be, when this is our rate parameter, it's going to be e to the power of negative lambda t times lambda t to the power of 0 over 0 factorial. These are both going to be 1. So the probability that y is equal to 0, that 0 events occur within a time interval of length t, is just e to the power of negative lambda t. So this whole expression right here is just going to be 1 minus e to the power of negative lambda t, where lambda in our case was 12 per hour. So you could just plug in 12 there if you want, and then you have to have t such that it relates to the time intervals over here, right? So we have like fractions of hours or multiples of hours, right? So this right here is the probability that big T is less than or equal to little t. So the probability that the first event occurs within the first basically t time interval. Okay, so now let's go on to part C. Okay, so we're going to use this result from part B. This is basically like the CDF of the exponential distribution, and we're going to derive the actual PDF of the exponential from that, which shouldn't be too complicated. Okay, now since we're dealing with a continuous random variable, right, time is continuous, to plot this, basically what we can do is we can have t on our x-axis, and then this function basically is going to look something like this. For a continuous random variable, if we're taking the probability that it's less than or equal to some value of t, so let's say our little t value is right here, well then that would just be the mass under this curve, where the curve is the probability density function, which we're trying to find. So we're trying to find this red function here, the PDF, and we're given basically the CDF, so the area under this red function up to this point t. So the blue area was calculated by taking the integral of the PDF, which we're trying to find. So fundamental theorem of calculus, all we have to do is take the derivative of this, right? So this is equal to the derivative with respect to t of 1 minus e to the power of negative lambda t, and this is really easy. The derivative of 1 is obviously 0, and then the derivative of negative e to the negative lambda t is just going to be basically negative of negative lambda times e to the power of negative lambda t, and then these negatives are going to cancel, so it's just going to be lambda times e to the power of negative lambda t. That is the PDF of the exponential distribution. So yeah, that's it. That's the PDF of the exponential distribution. It models the waiting time between events of a Poisson process. So this is an important one. You can see it wasn't too hard to derive once we knew the derivation of the Poisson from QP number 1. Yeah, this right here models the waiting time between events of a Poisson process. There's a lot of cool properties like memorylessness and stuff like that, which we'll get into later.